people. Like Vicki said, if you have questions, you can enter them into the question box, and as I'm going through, I'll try and answer them, or I'm happy to answer any questions at the end. So jumping into this project, what I'll be talking about today is a project that we did through CESTiCC titled Investigation of Alternative Deicers, specifically to look at the feasibility of using potassium succinate for roadway deicing. Really quickly, I'd like to acknowledge some really important people and organizations that were involved. Michelle Aiken was a co-author and really helped with a lot of the lab work. She was at Montana State University, and she's now at Washington State University, working with Sean Ming there. Again, this project was funded through CESTiCC UTC funding, so a huge thank you to them. And the match support for this project came from Minnesota DOT and their local road research board. And the first half of this project was really a synthesis to look at alternative deicers, which helped us identify succinates for this project. A huge thank you to BioAmber, which is the company that provided the potassium succinate samples and information to us, as well as Luft and to Connor. We used some of their equipment in the lab testing. So really jumping in, the objective of this project was to identify potential alternative deicers and then assess their performance and impacts and costs relative to what's commonly used. So in this case, the most commonly used deicer is still salt brine or rock salt. So that was really kind of our control and our standard throughout this test. So potassium succinate was identified as a product of interest in the preliminary work we did for Minnesota DOT. As I mentioned, it was a synthesis, and it was titled Field Usage of Alternative Deicers for Snow and Ice Control. And I provided a link previously, but you can also search for that report online. It's available. Now, that's not the first time that this potassium succinate has been suggested as a potential alternative deicer, and you can find those references in the synthesis for those early reports that really identified that. But previous work identified succinate salt as a deicing and corrosion inhibiting agent. And Berglund et al. 2001 and 2003 include some patent applications and a lot of the data that initially assessed potassium succinate as a deicing product. So looking into the background on potassium succinate, so it's been shown to be, potassium succinate has been shown to be the most effective deicer and corrosion inhibitor of the different succinate salts. And so that's why we focused on potassium succinate itself. And from the patent work and the early investigation by Berglund and his research team, they found that potassium succinate can penetrate ice similar to CMA, or calcium magnesium acetate. And when we talk about penetrating ice, the Strategic Highway Research Board, is that correct? The SHARP test methods, the 205 test methods, ice penetration is one of those tests. So it's kind of a common tool that's used to assess deicers. So those three tests that are part of that are ice penetration, ice undercutting, and ice melting. And so Berglund did those three tests, and we'll be comparing their results to our results in this work. So for ice undercutting, the tests for potassium succinate showed mixed results, which were average to better than average for potassium succinate compared to other deicers. And about a 2% concentration of potassium succinate when used as an additive to salt brine has been shown to reduce corrosion to steel by 40%. Now, increasing the percentage of potassium succinate did not improve the corrosion scores at all. So that's great news that you only need a small percent of this potassium succinate to really gain the benefits as a corrosion inhibitor. And other work by BioAmber and the company that has this product show that the experimental succinate-based deicer formulations have been certified for use on airport runways because of minimal corrosion impacts to concrete and metal infrastructure. So there is a precedent for using this product out there. Other background work for the patent application included looking at the impacts of biological oxygen demand. One issue with some of the deicers, like the acetate and the formate-based deicers that are out there, are that they exert this biological oxygen demand as the product is broken down. And what they found is that potassium succinate does break down in the environment, but it does exert a biological oxygen demand similar to acetates. And then just really quick, some cost data that was estimated by other researchers and by BioAmber suggests that the cost would be, in 2014 dollars, about $2.50 a gallon or $75 per lane mile, so not inexpensive. And BioAmber suggested that the potassium succinate would likely be on par cost-wise with formate-based deicers. But really, at this point, they have not scaled up their production, so they don't really know what that cost would be. They're just estimates at this point in time. Okay, so let's move into what we did. So we identified potassium succinate as a potential alternative deicer. And then what we wanted to do was maybe a deeper analysis or just supplement some more data to the past work that's been done. So we did the ice melting test, which again is that sharp test, but it's a modified test that we've done for years in our cold lab. And for the ice melting test, we set the cold lab temperature at about exactly 28 degrees Fahrenheit. For the products, what you do is you create ice lenses, you freeze them, and then you actually flatten them out and then you refreeze them. So you have a nice consistent ice thickness and ice surface. And then what we did is we compared a salt brine, 23% salt brine made with deionized water and reagent grade salt, and its ice melting performance to potassium succinate, which came as a 50% solution supplied by the vendor. Each sample was run in triplicate. As you can see here, this happened to be the picture shows the potassium succinate sample number 3, and the syringe we used to remove the liquid and the ice lens itself. Approximately 4.53 grams of liquid were added to each ice sample, and that includes all the ice samples run, so salt brine and potassium succinate. Again, they were run in triplicate, and what you do is you add the anti-icer solution to the surface of the ice, and then you go back after 10 minutes, 20 minutes, 30, 45, and 60 minutes, and you remove the liquid that's been melted, and you get a volume amount and a weight of that liquid, and then you add that back to the surface, and you do that essentially for an hour for each sample. Another test method we used a differential scanning calorimeter, or the DSC, and this allowed us to better understand the thermal properties of this product. So what we did is we took 10 microliters of a 1-to-2 volume ratio of potassium succinate to DI water, and then also our salt brine mixture. And again, the salt brine was deionized water and reagent grade sodium chloride. And what the DSC does is it heats and cools the product slowly over time, and it goes up to 77 degrees, and down to minus 76 degrees Fahrenheit. So a pretty substantial heating and cooling range. And we get to look at the thermal data from that. And last but not least, we also wanted to look at the performance of these products. So we did some friction measurements in the lab. And again, we used a cold lab temperature of 28 degrees Fahrenheit. And I neglected to mention this before, but the reason we used that temperature range was we knew based on that preliminary work that they did for the patent application that potassium succinate performs similar to CMA temperature-wise. And so we wanted to pick a temperature that would be a reasonable functional temperature for potassium succinate, but also for salt brine that we were comparing it to. For the friction measurements, what we have is we have a slab of asphalt pavement. We apply the anti-icer on top of the pavement. And so it worked out to be about 40 gallons per lane mile for the application, which is a very reasonable anti-icer application rate used in the field. Again, we used salt brine made with reagent grade salt and deionized water, and we used the potassium succinate as supplied by the vendor. We then added 800 grams of snow that's made in the lab. It sits for a couple days to equilibrate. And it essentially looks like grapple, and then it's sieved down to a similar grain size. So these 800 grams of kind of similar grapple-sized snow are added to the pavement surface, and then they're compacted for about 5 minutes, and it creates about a ½ inch thick snow layer. We then traffic these samples, as you can see in the picture, with that tire rolling over the pavement sample. And here's some of the specs on the trafficking. It's about 1 foot per second. The vertical load is equivalent to a vehicle, or as close as we could get to it. And we traffic the samples for about 500 single tire passes, or just under 20 minutes. And this is a lab testing methodology we've done for quite a few projects now. So we've kind of honed in on what works well. So moving forward with the testing, we're not done yet. So now that we've trafficked those snow samples, we then plow the snow off the pavement. And then once that snow has been plowed off, we can then measure friction of the pavement surface. So we collected friction data at 4 different points throughout this testing, and the stages are listed below here. So the first data collection point, or stage 1, is the dry pavement, so the clean, controlled asphalt pavement at that 28 degrees temperature. The stage 2 is after you've anti-iced and you've added the snow and you compacted it, we measure friction then as well. And then we also measure friction after we traffic it, and again after we plow it. And I just made a note here so you guys are aware of the data volume that was collected. So friction measurements were collected at all these different stages, but at stages 1 and 4, we collected at 6 locations per sample, and at stages 2 and 3 at 3 locations. More because it's easier to collect the data on the dry pavement and then after plowing than it is to collect it on the snow surface itself. And last but not least, we collected friction data using 3 different techniques. We collected static friction, which is a manual technique that's used in the lab, and gets you a single data point, so you have to do that in replication. And then we also used the Luff-Marwis and the Taconnor RCM411, which we had in the lab for another project, and we were able to use for this one. And so this picture, you can see the mount of the Taconnor unit over the asphalt sample. And the great thing about these mobile units is that you can collect friction data on any surface condition, and it's continuous data. So the volume of data is just much higher. In addition, they also collect other data points like pavement temperature and whatnot, but we won't go into that in this paper. Okay, so what does all this data tell us? Well, here's the ice melting test results. So again, these were measured at 28 degrees Fahrenheit. This is where you You add your deicer or anti-icer to that ice lens, and then you measure how much is melted over time. So on the x-axis, you have time from 0 to 60 minutes, and on the y-axis, you have ice melt in milliliters per gram of deicer. So what you can see here is in gray, we have our sodium chloride, salt brine, and in the blues, we have our potassium succinate. So generally what we found is that salt brine showed a slightly higher ice melting rate than potassium succinate at 28 degrees Fahrenheit. And for both products, the ice melting began within the first 10 minutes. And so I'm going to go back and you can see here that from 0 to 10 minutes, they both had a very equal jump in ice melting. So that's good. That means they're both initiating that ice melting at similar times. And then also the ice melting continued for both products for the full 60 minutes, but at a decreased rate for potassium succinate. So again, I'll go back so you can see. And what you can see with the salt brine and the grays is you have that big jump at 10 minutes, and then you have a slow, steady, consistent ice melting rate that slowly increases through the 60 minutes. It's a little more variable for the potassium succinate in blues. You get that jump in ice melting up to 10 minutes, and then overall, on average, for all the potassium succinate replicates, you have a melting rate that is continuing for the 60 minutes, but just at a decreased rate compared to the salt brine. So another way to look at this data is just in a table, and generally what's reported is the ice melting rate after the 60 minutes. So what you can see here is that for potassium succinate, 2.6 milliliters per gram were melted, whereas for sodium chloride, 3.15 milliliters per gram were melted. So again, a significantly more greater amount was melted with the salt brine than the potassium succinate, but again, not by a huge amount. All right, and looking at the data and comparing it to work by other folks. So you can see here on this graph that we're looking at ice melting again, and on the x-axis, we're looking at the different test temperatures that were used. So in the kind of green-blue at 28 degrees, that's the testing we did. And then at 20 degrees and 5 degrees, that was testing by other folks of the same product. And what you can see here is a consistent trend of at warmer temperatures, you get more ice melting. And that's generally what you see for just about any deicer. Moving forward. All right, so let's look at these DSC results now. So what we're looking at, and again, this is the thermal analysis of these products. So what we like to report is T sub C, which is the characteristic temperature, which is the temperature at which ice crystals begin to form in that liquid. For salt brine, that's about 5 degrees Fahrenheit or minus 15 Celsius. And for potassium succinate, that's about 22 degrees Fahrenheit or minus 5 degrees Celsius. Now, this is just the temperature at which ice crystals form. So if you went out in the field and you told a garage supervisor that he should be using salt brine at 5 degrees Fahrenheit, he will disagree with you. Generally speaking, the characteristic temperature or the actual functional temperature of salt brine is going to be about 15 degrees Fahrenheit. So this is really just the lowest possible temperature you'd really want to use these products at. But what can we say from this? Well, in the field, this translates to the effective temperature or the lowest temperature limit at which the material remains effective within a 15 to 20 minutes of application. and that the lowest temperature a deicer should be used to achieve effective ice melting. So again, salt brine appears to work as a deicer at colder temperatures than potassium succinate. And if you are using a 50% solution of potassium succinate, it should not be applied for deicing purposes below 23 degrees Fahrenheit.
Laura, my screen hasn't advanced since the ice melting test results first slide.
Uh-oh. I've been advancing. That's a bummer. Okay, let me see if I can escape out.
Yeah, it seems there. I noticed a little lag early. Sorry for the interruption, folks. I just want to make sure people are seeing what Laura thinks what Laura's talking about.
Yeah. Okay. What slide are you guys seeing now, Vicki?
I'm seeing the side that has results, ice melting test. I think it's your first of your ice melting test results slides. It's the 28 degrees ice melt on the X time on the bottom.
Okay. And are you seeing it at advanced now?
No, it's just on that one. That's bizarre.
Okay. Do you want to regain control and then give it back to me and see if that helps?
Sure.
Okay.
Let's see if that. All right. Do a quick show my screen. And then let me. There we go. Okay. And then. All right. Now let me. Okay. All right. Let's see if I can. That's bizarre. Webinar. The GoToWebinar is updating. Well, let me change presenter back right now.
Okay.
Running through audience view from red to green multiple times here, so it might be a problem at their end. All right, I'm going to stop showing screen for a moment. So we're going to go back to the intro screen, see if that calms down. Laura, it says that you're not connected anymore.
I can still hear you.
I know, but when I look under the webinar thing, it shows you as not being on. So I can't change the presenter back to you.
Okay, let me bring this up. You have recordings that need to be converted before anyone can view them.
Oh, so were you recording also? Okay.
I wasn't also recording, I think.
Yeah, that's something it should give to me. So, yeah, somehow it kicked you out. Our apologies for the technical difficulties. We'll resolve this.
Okay, let me get back in. All right, am I showing up now? Oh, it wants me to call in with a different audio pin now.
All right, well, why don't you hang up and then call back in again?
Okay, I apologize, folks. Let's see if this works.
Yes. All right. Well, while Laura's doing that, I will take this opportunity for an announcement that if anybody wants continuing education credit for this hour, please send me an email and I will provide you with a certificate of attendance for this webinar.
All right, can you hear me now?
Yes, I can hear you. And now I have the option to make you presenter again.
Okay.
All right. Yep, I've made you presenter.
Okay, so I apologize, folks. If you bear with me, I will run through these slides again. I want to make sure you can see them advanced, though, before we get Vicki off on mute. Okay, can you see, did the slide advance?
Yes, the slide advanced that time.
Okay, so let's do this again. I apologize. Okay, so looking at the results, we're looking at our ice melting test. We're at 28 degrees Fahrenheit in the cold lab, and on the x-axis, we're time, and on the y-axis, we are ice melting in milliliters per gram of deicer. You guys had a lot of time on this slide, so I'll move to the next one. So generally what we're seeing again is that salt brine showed a slightly lower ice melting rate, or a slightly higher ice melting rate than potassium succinate, that the ice melting began within the first 10 minutes for both products, and that ice melting continued for the full hour of the test for both products, but at a decreased rate for potassium succinate. And then looking at the data in a different way, we're just looking at the final ice melting capacity at the end of the test. And again, what you can see here is that sodium chloride had a statistically significant greater ice melting capacity at 28 degrees than potassium succinate, which are those at 60 minutes, the red circled values. And then looking at ice melting capacity data in a different way, what we're looking at here is a figure with 3 different data sets. The data we collected is in the turquoise bar at 28 degrees Fahrenheit on the x-axis. And we're just comparing that to data collected by other folks, mostly from the patent application. And again, what you see here is that potassium succinate melts more ice at warmer temperatures. And the trend is very consistent, which is great. That tells us that the data that we've collected is good and in line with what other folks have collected. And this is a trend that you see similarly with other deicers. Okay, now moving on to the Dsc results. So what we're looking at here is the characteristic temperature of the data, and this is that thermal analysis of these products. And the characteristic temperature represents the temperature at which ice crystals begin to form in solution. And so for salt brine, the characteristic temperature is about 5 degrees Fahrenheit or minus 15 Celsius. And for potassium succinate, it's about 22 degrees Fahrenheit or about minus 5 Celsius. And what this means is that in the field, this translates to the effective temperature or the lowest possible temperature limit at which this material remains effective for about a 15 to 20 minute period following application, and would be the lowest temperature a deicer would be used to achieve ice melting. And what we see is that salt brine works as a deicer at colder temperatures than potassium succinate. And if using potassium succinate, a 50% solution should really not be applied for deicing purposes below 23 degrees Fahrenheit. Okay, now we're caught up. So now we're into the friction results. So again, we're looking at performance of these products. What we have here is a graph, and again, it's showing those 4 stages of testing that we talked about. Again, stage 1 is that clean pavement at 28 degrees Fahrenheit. Stage 2 is the ice or the snow compacted. Stage 3 is the trafficked snow on the pavement. And stage 4 is after plowing. You can see friction on the vertical axis. And there are a lot of different colors going on here. But again, I tried to stick to potassium succinate data in blue and sodium chloride salt brine data in grays. And generally what we see is that performance of potassium succinate is similar to salt brine at improving friction on roadways. Both products show the same overall trend of friction values starting high on the pavement at stage 1, and then friction values dropping with anti-icing and the addition of snow and compaction of snow at stage 2. And then friction values remaining low as the snow is trafficked on the pavement surface, and then friction values then increasing after plowing of the snow from the pavement surface. So I'll just go back so you can see that, again, great friction in the beginning, and then friction drops and would make perfect sense as you have snow and ice on the pavement surface. And then after you plow the material off, friction values increase again. They don't always return back to where they were, but they do generally increase. So another thing that we generalized on the graph are these different color zones for the friction values, where green represents a reasonable friction for the driving surface. The yellow zone is a reduction in friction to more slippery conditions, and the red zone represents an even greater reduction in friction to consistently slippery or icy road conditions. And I'll go back so you can see that again. And these are just generalized zones so that we can kind of categorize what would be a safe driving condition and what wouldn't be. And really what you can see here is at stage 4, you have this return to more safe driving conditions, whether it's in the yellow zone or the green zone. So both products show a return to higher friction values, whether it's green or the yellow zone, or less slippery conditions following plowing. But there does not appear to be a clear trend of one product performing better than the other. And this may be variability in the test methods and between the different friction measurements and methods, which make it more challenging to see the relative performance of each de-icing product. So what can we say about this testing? Well, performance of potassium succinate is similar to that of salt brine at improving friction on roadways. The thermal analysis shows that potassium succinate can be applied as a roadway de-icer at temperatures of 23 degrees Fahrenheit or warmer, and that potassium succinate shows a slightly lower or reduced ice melting rate than salt brine. Previous work that's been done has shown that potassium succinate has no corrosion impacts to metal, equipment, or pavements, and that the BOD exerted by potassium succinate is similar to that of potassium acetate. Potassium succinate may be considered for application in areas where there are concerns about impacts to infrastructure, equipment, or pavements, such as on bridges, elevated roadways, in parking garages, or on newer concrete pavements. And overall, potassium succinate performs as a de-icer, but at warmer temperatures than salt brine and with slightly less ice melting capacity, but with similar friction performance to salt brine. And again, potassium succinate appears to be a viable option as a roadway de-icer at warmer temperatures or temperatures above 23 degrees Fahrenheit. Interestingly, work by other folks towards getting the patent application and other research projects has found that potassium succinate, when blended with other de-icers, can be effective at colder temperatures and you still achieve the corrosion inhibition. At this time, there are some limitations with this product, and partly cost is unknown. It's estimated to be similar to acetates and formates, but again, until production is scaled up, they won't know. Because production has not been scaled up, it's not available in large quantities at this time. But again, that could change quickly if the market drives the need for it. And we recommend additional testing to further quantify potential environmental impacts, but also to better assess product performance. So thank you for sticking with us despite the technical difficulties. I would love to take any questions at this time. And here is the link to the final report that's on the CESTiCC webpage. So I think someone just came on the line, but I couldn't quite hear. So I'm going to go through maybe the question list. Thank you, everyone who let us know that the slides were not advancing. Yes, the slides will be available, I believe, on the CESTiCC website, and the webinar, despite its technical difficulties, has been recorded and will be posted to the website as well. Is that correct, Vicki?
Yes, that is absolutely correct. And I'll post the slides and the webinar here in a bit.
Okay, and then
I'll post the slides as soon as Laura sends them to me.
Great. And then Danny asked, how was the manual friction test done? Was it done with the British Pendulum tester? No, it was not. We developed a method, and it's better explained in the report, and there's even pictures of it in the report. Essentially, we have a metal frame with a weight on it, and we pull at a consistent strength, and you measure the amount of friction it takes to overcome moving that weight a certain distance. And if you want to see very specific pictures of it, I'm happy to share those with you, Danny.
Okay, any other questions? Either entered on the question pane or online?
Yeah, there are a few more questions entered in the question box, and I'll go ahead and answer those. And if folks have questions to follow up or just on the phone, I'm happy to answer them. So another question asked is, this new product is applied in solid format, correct? Can this be used as a liquid? So the potassium succinate that we received was in a liquid, and I think they would prefer that it's used as a liquid as an anti-icer. In terms of solids, I don't know. I'd have to talk to the company to see if they produce a solid formula of this. And I think those are all the questions that were posted online. So any other questions from folks on the line?
Either unmute, or if you're self-muted, or raise your hand and if you're muted by me. If not, thank you for attending. Oh, there's somebody's raised their hand. Got it. Okay, go ahead, Alani.
Thank you for the presentation. Was the resistance to deicing scaling performed with this potassium succinate? Because the only result that is presented is the friction resistance for it and the melting capacity. Like if there is any test conducted on the deterioration of the concrete using the surface de-icing scaling resistance?
So that's a good question. So I think what you're asking is, did we do any additional scaling or impacts to concrete pavements testing?
Yes, please.
And
yes, please.
no, we did not. So this project was a fairly small budget project. So we wanted to do testing maybe that hadn't been done yet. And other folks have done some corrosion testing on this product. So we kind of deferred to that past work to cover that. But scaling testing would be great for this. I do know that it is approved to use at airports. So I'm guessing that if they've seen the concrete corrosion data and they like it, it's probably has little to no scaling. But again, there's always room for more testing, right?
All right. Anyone else? Okay. Well, thank you all. Thank you, Laura, for this presentation, and thank you all for attending. I will be posting both the slides and the recording of the webinar on the website later today, and hopefully there will be additional CESTiCC webinars in the future for your enjoyment. So thanks a lot.